My name is Elyse Pennington, and today I will be talking about a new model to represent secondary organic aerosol formation from volatile chemical products. As emissions from vehicles have declined, emissions from other anthropogenic sources have become increasingly important, including emissions from volatile chemical products, or VCPs. VCPs are described by the categories shown here and consist of many different products with different compositions that contain organic solvents, which emit organic compounds to the atmosphere. And because of the wide array of products and compositions available, VCPs emit hundreds of different species. And some of these are understood to form SOA, but many have not been studied in laboratory settings. And so it is very uncertain how much SOA is formed from these VCPs. And so that's demonstrated in this figure here from a recent study by Mo Chin et al., which added VCP emissions to the NEI and used a top-down approach to estimate how much SOA is formed from those VCPs. And so what we have on the left in the blue shaded region is the current NEI predictions of both organic gas emissions as well as the mass of SOA that they're expected to form. And then on the right, we have the results of this study. And so we see that the total organic gas emissions increased with the addition of VCPs. And we also see that the impact on SOA can be very large. And so the mass of SOA formed depends on how the chemistry of these organic gases are treated. And so using this top-down approach, this paper was able to estimate how much SOA they think is formed from VCPs. And so our goal was to develop a bottom-up approach to understand the same process of SOA formation from VCPs. And so today I will briefly talk about emissions from VCPs, as well as the properties of the species that are emitted and how they form SOA. And this is with the goal of developing a model to implement in CMAC. So first, I'll talk about a new emissions inventory known as VCPI. This was developed by Carl Seltzer at EPA, and I encourage you to check out his presentation to learn more, but I will give a brief introduction here. So VCPs can be divided up into product use categories, or PUCs, and these are the different categories that I showed before, which include personal care products, cleaning products, pesticides, etc. And each PUC can be further divided up into sub-PUCs depending on how they're used. So for example, some products may be used daily and others may be used monthly, and so those would be in separate sub-PUCs. And then within each sub-PUC, Carl used product usage data and product composition data to find the composition of the sub-PUC as a whole. And then for each species, by comparing the time scale of evaporation with the time scale of product usage, was able to calculate an emission rate. And so VCPI outputs emission rates for about 400 different species. Once we had this list of species and their emissions, we wanted to understand their chemical and physical properties. And so we created a large table of properties for all of the 400 species. And so what I'm showing on the left of each of these flowcharts is a few of the properties, and then on the right is the information that they provide relevant to SOA formation. And where experimental data was available, we used that, but in many cases, experimental data isn't available because many of these species that are emitted from VCPs have not been studied extensively. And so in those cases, we needed to estimate their properties using QSAR models, which are quantitative structure-activity relationship models, and those are listed here. And so a few of the things that I'll talk about today are boxed here. One of them is the SOA yield, which is defined as the mass of SOA formed per mass of VOC reacted. and this often relates to the oxygen to carbon ratios of the parent precursor, as well as the volatility, or C star. In this figure on the right, we have SOA yield versus log of the volatilities for all 400 VCP species. And what we see is that the volatilities span a very wide range. And we also see that the SOA yield increases as the volatility decreases, which we'd expect. Like I mentioned, we used experimental data where available, but for many of these compounds, we had to predict their SOA yields using the statistical oxidation model. If we average the yield over all the species and weight by location-specific emission rates, we can calculate a net or effective SOA yield. And so if we do that for Los Angeles County, we get an effective yield of 5.6%. And this is very close to the value predicted by the top-down approach that I mentioned earlier. And so because these two approaches produce similar results, we feel fairly confident that our SOA yields are fairly accurate. And so the next step is to represent this SOA formation chemistry in a model. And so what is shown here is the same figure as the previous slide, but now the species are colored by their assignments within our new model. So the compounds in blue, which I labeled as traditional, are species that are routed to existing surrogates in CMAC. And so I'm not going to go much into detail with these, but I will talk more about the other three categories, which are new pathways that we're going to add to CMAC. So first, we have non-oxygenated IVOCs in orange, and we see that these generally have lower volatilities and pretty high SOA yields. The other two categories are oxygenated IVOCs and siloxanes, and siloxanes are a type of oxygenated compound. So the reason that we separated them from the rest of the oxygenated compounds is because they have relatively high yields and emissions, but they have very low OH rate constants. And so we found that our model performed better when the siloxanes were treated separately from the rest of the oxygenated IVOCs. Here is a summary of the three new models. So at the top, we have siloxanes, and we used a two-product model from Janacek et al., and this model oxidizes the gas phase precursor into semi-volatile oxidation products, which partition between the gas and aerosol phases. And this existing model fit our data well. Next, we have the oxygenated IVOCs, and here we have a single precursor and product with a constant SOA yield. And so the reason we're using this fairly simple model is because, as I mentioned, many experimental studies haven't really been performed yet to understand how these oxygenated IVOC precursors proceed through atmospheric oxidation to form aerosol. And so we have yield values, but we don't have much other information about the product distributions. And so for now, we're using this fairly simple model. And then lastly, we have the non-oxygenated IVOCs. And for these, we used an existing model by Chanyang Liu, which was parameterized based on mobile IVOCs. And so this model splits up the gas phase precursors into 6 different surrogates that are divided up based on their volatility and structures. And then those precursors undergo a multi-generational aging scheme to form aerosol. And so our non-oxygenated IVOC VCPs had similar properties to the mobile IVOCs, so we applied this existing model. And the emission rates of all of those gas phase precursors are informed by the VCPI emissions. And so if we look at the annual totals, we see that about 70% of the emissions are from traditional species, which are the species routed to existing CMAX surrogates. And the remaining 30% goes to these three new categories. And so I'll just note that the most of the emitted VCP mass is oxygenated IVOCs. This model was implemented in CMAC version 532 beta, and simulations were performed over a month-long period in summer 2010 to overlap with the CalNext campaign. I'll be showing the results from two different simulations. The first is noted as base, and it uses the configuration from the previous slide, and it has PCSOA removed, for those of you familiar with CMAX chemical mechanism. And then the other simulation is noted as plus VCP. And so this has the three new VCP IVOC pathways, but does not have the mass going to traditional species. And this is because we realized that the speciation profiles that we were using weren't working exactly how we wanted, and so updating those speciation profiles is up next on our to-do list. So looking here on the left, we have the PM1 SOA predicted by the two simulations compared to observational AMS data from CalNext. And we see that while the SOA is still underpredicted, if we zoom in on the two simulations and look on the right, we see that the SOA was actually doubled in the plus VCP case. And so that is a significant improvement. And if we look at which of these new pathways is contributing most to this new SOA, we see here on the right, which is a bar chart of the noon time SOA concentrations averaged over the month-long CalNext period. We see that most of the new SOA mass is coming from the non-oxygenated IVOCs, with still noticeable amounts coming from the siloxanes and oxygenated IVOCs. And we can go back to this bar chart showing the VC-pi emissions and note that even though the non-oxygenated IVOCs didn't have the greatest emitted mass, because their SOA yields were so high, they formed the most SOA. So to conclude, we saw that the noontime SOA mass in CMAC increased by about 2 micrograms per meter cubed with the addition of these three new chemical pathways for VCP IVOCs. And we feel confident that these three new categories of siloxanes, oxygenated IVOCs, and non-oxygenated IVOCs should be treated separately in the model because of their unique SOA yields and emissions distributions. And we expect a greater SOA increase once we implement the updated speciation profiles that will accurately map the explicit VCP emitted species to CMAX surrogates. And so we'll be working on that, as well as working on creating gridded emissions files from VC-pi to improve our spatial and temporal results. And lastly, as I mentioned, a lot more studies are happening now to try to understand the SOA formation from these newer sort of SOA precursors coming from VCPs. And so as the community learns more about these, we'll be updating our model to better represent this chemistry. And with that, I would like to acknowledge these people and funding sources, and I thank you for listening.